everyone. We are doing chapter 19, which is Transition Metals and Coordination Chemistry. So this chapter only has 3 sections, but they're fairly long, so don't let it fool you. We have the occurrence, preparation, and properties of transition metals and their compounds, coordination chemistry of transition metals, and spectroscopic and magnetic properties of coordination compounds. So we're going to start off with 19.1, the occurrence, preparation, and properties of transition metals and their compounds, and that's basically our learning objective also. Here's just kind of a start for you. These are some beautiful complexes. Transition metals tend to form these beautiful colored complexes. You have malachite, azurite, and prostite. And we're going to talk a little bit about how they form these colors. That'll be in 19.3, but we're going to talk more about the complexes that they form in this section. So transition metals themselves are defined as elements that have or readily form partially filled d orbitals. So, we have S block, we have P block, and then we have D block. So these can be the D block elements, groups 3 through 11. We also count the F block elements, which are also called the inner transition metals, the lanthanides and the actinides. Those are the two groups kind of that are below the main part of the periodic table. Group 12 technically are not transition metals, and that's because they're actually full. They're not a partially filled d orbital, but because they do display some of the chemical properties of the transition metals, a lot of times they're treated as transition metals or just kind of included in the discussion. So we have some transition series. The first transition series, which is the period 4 elements, so this is scandium through copper. The second transition series, which is yttrium through silver. The third transition series, which is lanthanum, and then it goes to hafnium through gold. And then lastly, the fourth transition series, that's be AC, not just A, which is actinium and rutherfordium through roentgenium, which most of those are synthetic elements. So we also have the F block elements. We have the lanthanide series, which is technically cerium through lutetium. Lanthanum itself, which is the element right at the start, it behaves like a lanthanide element, so it's considered one, even though its electron configuration technically makes it the first member of the third transition series. Then we have the actinide series, which is thorium through lawrencium, and actinium, kind of similar to lanthanum in that it behaves like a, not a lanthanide, an actinide element. So it is technically considered one, but it is also the first member of the fourth transition series. This is just kind of a picture of the periodic table from your book. So the transition metals are groups 3 through 11, so we're talking about right here. And then we have the inner transition metals at the bottom. So again, technically group 12 are not considered transition metals, but a lot of times they're included in the discussion because sometimes they do behave similarly. Okay, so here's an example. This is a good refresher for chapter 6, which is electron configurations, and also is going to be very helpful to us for the remainder of chapter 19, and that's doing some electron configurations. And this wants us to do some electron configurations for these ions that are transition metals. And they do give us a nice reminder that whenever there's S electrons, those come off first before the D or F valence electrons. And then it wants us to give the electron configuration for these ions. Okay, so the first one we're given is cerium. We're told cerium 3, but let's first look at the neutral atom. The neutral atom of cerium is 58, based off its atomic number. So to do the electron configuration for just cerium, we would notice that xenon is the closest noble gas, and xenon is 54 electrons. So that would take care of 54 electrons for us. And we also can see that xenon is full up to the 5p orbital. It's in p block. It's in period 6. It's in period 5, which means the 5p orbital is full. So that means that we would go to the next orbital after 5p to fill it up for cerium. And if you were to look at figure 6.24 in your book, highly recommend you mark this page or something. You find that after the 5p orbital is filled, the next orbital is 6s, which the s orbital holds 2 electrons. Oops, not that. So we would go up to 6s2. And notice there's a difference of 4 electrons between neutral cerium and xenon. So that took care of 2 electrons. So now we have 2 more electrons. And the next orbital after 6s is the 4f orbital. So that brings us to 4f and then 2. The f orbitals can hold 14 electrons, but in this case there's only 2 left, so it ends at 4f2. Now, since this is cerium 3, that means we have a charge of 3+. So we need to go ahead then and get rid of 3 electrons. So since the s electrons come off first, that means these 2 electrons are gone from the 6s shell, so it's going to be gone. And then one of these f orbital electrons is gone. So for cerium 3+, we get xenon 4f1 for our final electron configuration. And then this is in the lanthanide series. It's in that inner transition metal in the top row, which means it's in the lanthanide series. Okay, the next one is lead 2. So going back for lead, we find it on our periodic table, and we see that lead, where are you, lead? Pb lead is a main group element, so it's not a transition metal. It is in group 14, and it is in the p block. So for neutral lead, we would have xenon as its closest element, because lead is element 82. And then after xenon, we go from 54 to 82 electrons. So we have 28 electrons now to play with. And xenon, just like in cerium, it's filled up through the 5p orbital. So we're going to start with 6s, and we have 6s2. So there's 2, and then 4f14. Which, by the way, in your book, there also is a very helpful electron configuration table. Figure 6.29 is also very helpful and gives you the electron configuration for neutral atoms. And then from the F, we go to 5D, 5D10. So that is 24, 25, 26. And we have 28 electrons in total. So now the next orbital we go to is the 6p orbital. So then this goes to 6p2. So that is the neutral lead electron configuration, but this is lead 2+, so that means that we need to take off 2 electrons, and these are actually going to come from the p orbital in this case, because that is actually our valence orbital. So then this becomes xenon 6s2 4f14 5d10. And again, this is a main group element in p block and in group 14, but lead can kind of behave like these transition metals since it has both a D and an F block. It can do some weird things too. All right, our next guy here is titanium 2, and titanium is element 22. It's in our first transition series. So neutral titanium's closest noble gas is going to be argon. Argon has 18 electrons, titanium has 22. So now we're going to go ahead then and go up from argon, which is the 3p orbital that's filled up, and the next orbital then is the 4s2, and then up to 3d2 since we have 4 electrons. But here, since this is titanium 2+, that means we need to get rid of 2 electrons, and they're going to come out of the s orbital first. So then that leaves us with argon 3d2. And again, this is in the first transition series. Down to D, we have americium 3. And this guy is in the actinium, or the actinide series, so it's by actinium. It's element 95, so we have 95 electrons when we're neutral. And because of that, our closest noble gas is radon. So we have Rn. And radon is actually filled in the 6p orbital. So, and that has 86 electrons. Americium has 95. So we have then 9 electrons to play with. So after the 6p orbital is filled, we go up to 7s. And from 7s, we go up to 5f. And that's going to be 5f7. Now we are getting rid of 3 electrons, which means the s electrons are gone and one of our f electrons is gone, down to 6. So for americium 3+, then we have radon 5f6. And our last example is palladium. Palladium is in the second transition series, and we want palladium 2+. Palladium has 46 electrons. Its closest noble gas is going to be krypton with 35. So that tells us for neutral palladium, we have 11 electrons to play with. Krypton is filled to its 4p orbital. So the next orbital after palladium, I just like saying palladium, it's kind of fun. Palladium's kind of a weird guy. Normally we would go up to 5s for 2, and then we would go to 4d for 8. But palladium is actually bizarre. Instead of doing that, the electrons actually all go up to the d orbital, and so this just goes to 4d10. And then since it's got the +2, this becomes an 8, so we have krypton 4d8. So definitely mark chapter 6 in your book, figure 6.24, 6.29. even 6.27, these figures are going to be very, very helpful for you for starting with getting your neutral electron configuration. Like I said, it actually gives you them in figure 6.29. And then in 2.4, it gives you the energies of the orbitals, and 6.27 shows you the orbitals also. Oh my gosh, yay! I just got a text that my foster is able to, oh, not my fault, my foster dog has an adopter. All right. So we've identified the series for all these metals also, and now we've done their electron configuration. So hopefully this helped you. I know these can be a little confusing. Just remember chapter 6 will be your best friend with these, but you should be able to do these, especially with the aid of chapter 6. So I just thought I'd show you this figure 19.3. This is from Chemistry in Everyday Life, talking about lanthanides are actually used in some electronic devices. They are often called rare earth elements, but they're actually fairly abundant in the Earth's crust. We have 17 rare earth elements, and which is 15 of them are lanthanoids, and the other 2 are scandium and yttrium. We call them rare because it used to be very hard to extract them to have a pure sample, but it's become a lot easier nowadays with new separation methods. And things that they're used for is quite a lot. Europium on the left there is used for flat screen displays, for computer monitors, cell phones, and televisions. Neodymium magnets are found often in hard drives. And they also are used for converting crude oil into gasoline. Another example is holmium is found in some dental and medical equipment. And then some alternative energy techniques also need lanthanoids. Like neodymium and dysprosium are used for hybrid vehicle engines, and the magnets that are used in wind turbines. So for instance, I drive a hybrid car. I have a Subaru Outback that's a plug-in hybrid, so it probably has some rare earth metals in it. So yes, one more. Things are back to campus. If you ever see a bright blue Subaru Outback with a license plate that says AV Heart Chem, that's probably me. So we're going to talk about some of the properties of the transition elements. They do have some general properties in common with most of our other metals. They tend to be hard and have high melting points. They tend to be good conductors of heat and electricity and can form alloys. And they generally lose electrons to form stable cations. Now, one thing that's interesting about them is they don't necessarily always form just ionic bonds. They tend to form stable coordination compounds, and these have a central metal atom or ion that acts as a Lewis acid and can accept one or more pairs of electrons. There's a bunch of different molecules and ions that can serve as the Lewis bases that donate electrons to that center metal. We're mostly going to be focusing on the first transition series metals in this chapter, but here and there we'll sprinkle in some of the others. All right, so some more properties about them. They tend to have varying reduction potentials. Some of them are very strong reducing agents. Some of them aren't very reactive. So, for instance, things like gold and silver and platinum really aren't that reactive. But there, like I said, some can be very strong reducing agents, such as well, beryllium and magnesium are our main group, but they can have the reduction potential of something like a beryllium or magnesium and be very strong. The lighter D block elements, so like the ones from the first transition series, can form very colorful and hydrated ions that are water stable, such as like chromium 3+, iron 3+, cobalt 2+. These tend to be very colorful. But if you go just one period down, and the ions tend to be unstable. So like molybdenum 3+, ruthenium 3+, iridium 2+, they're very unstable, and it will react very quickly with oxygen from the air. But those heavier D block elements, to be water stable, tend to be oxyanions instead. So such as molybdate, which is MO04 2 minus, and rhenium O4 minus. So just some examples. We have a group called the platinum metals, which include ruthenium, osmium, rhodium, iridium, palladium, and platinum. And these don't form stable oxyanions, and it takes some energy to make them form simple cations that can be stable in water. It's difficult, but it can happen with enough energy and the right stuff. Both our D and F block elements will react with nonmetals to form binary compounds, but a lot of times you need to give them some heat so they have some energy to get over that activation energy barrier. They can form a bunch of different halide compounds that have oxidation states that can range from 1+ up to 6+ for the metal. They'll react with oxygen with heat, except palladium, platinum, silver, and gold. And for those of you that are jewelry aficionados, you'll notice that those are the 4 main types of metals that are used for jewelry, or like for more expensive luxurious jewelry, if you will. Palladium is just recently coming out more. I'm a big fan of palladium for jewelry. Palladium and platinum tend to be my favorites because they're a little more tough, but they're also more expensive. So then we have F block, group 3, and the first transition series, except copper, will react with aqueous acids, and those will form hydrogen gas and aqueous salts. And it's kind of a good thing when you think about it for copper to not react with aqueous acids, because copper is also used in things like jewelry and cookware. So if it reacted with aqueous acids, you know, we wouldn't have a good time trying to use it in everyday life. Now, our transition metals have a wide range of oxidation states. If we're looking for scandium through manganese, from our first transition series, their highest oxidation state corresponds to the loss of all the electrons from both their s and their d orbitals of their valence shell. And this is actually the most stable form for scandium, titanium, and vanadium. But after manganese, once we start at iron, we actually can't remove all those valence electrons. So the number of oxidation states that they can form decreases. So it's interesting. We'll look at the figure, I think it's on the next slide, but the number of oxidation states increases as we start from scandium going up to manganese, but then after manganese, the number of oxidation states goes down. So it kind of does this. The second and third transition series tend to be actually more stable in higher oxidation states than the first series. And this is because the atomic radius of them is bigger, since these now have more electrons and have more stuff in them, and now they can have larger ions. So because there's more space now between those electrons and the nucleus, it's easier to pick those extra electrons off. So this is the little table I was telling you about, and this is showing the oxidation states, the common oxidation states of the first transition series metals. So you can see that scandium over to manganese, the number of oxidation states is increasing, but then it starts decreasing as we go from iron to zinc. And that's because we can no longer pull off all of those valence electrons. So we have an example here. We want to know what the strongest oxidizing agent is in acidic solution. So we have dichromate ion, which has chromium 6, permanganate, which has manganese 7, or titanium dioxide, which has titanium 4. So a way to start is look up the reduction half reactions for each of these oxides in their oxidation states. So for dichromate, that reaction is Cr2O7 2 minus plus 14H plus 6 electrons gives us 2Cr3 plus 7H2O, and it has it's 1.33 volts. For permanganate, we have MnO4 minus plus 8H plus 5 electrons going to Mn2 plus water, and this is positive 1.51 volts. And then for titanium dioxide, we have TiO2 plus 4H plus 2 electrons gives us Ti2 plus 2 waters, and this is negative 0.50 volts. So a larger reduction potential means it's easier to reduce, which then means it's a stronger oxidant or oxidizing agent. So that means that permanganate is going to be number 1, then dichromate, and then titanium dioxide. So 1, 2, 3. So now we're going to talk about how to prepare copper, silver, and gold. We're not going to talk really much about preparing the others, just kind of talk about some and then we're talking about an elemental form. We're going to talk about some of their other forms too, but starting with their pure elemental stage, we can find some of these metals, like copper, silver, and gold, in their elemental forms, in ores. Sometimes they're in like veins. Ores are the best. Iron tends to be a little different. Sorry, when I misspoke. We're going to be looking at making iron, copper, and silver, I believe. Yeah. We use smelting to extract the pure element of iron from the naturally occurring ore. Iron tends to come in exclusively in its oxidized form, such as rust, Fe2O3. What's interesting with the D block ions is it's really not that difficult to reduce them to their free elements. And a lot of times all you need is carbon to be used as a reducing agent. There are 3 main steps to isolate most of these D block metals. The first is preliminary treatment to make them suitable for extraction. And a lot of times this can be crushing or grinding it so it's easier to melt, or concentrating those metal bearing components. Sometimes you do a chemical treatment to convert them into compounds that are easier to reduce into the metal, but it's just, again, getting it ready to be extracted. The next step is smelting, which is going to take that metal and convert it into the molten state of the ore. And this is also where they reduce it to its metallic form. While molten, sometimes impurities can be removed with a compound to form what is called slag. And slag is a substance with a low melting point that can be readily separated from the molten metal. And the last step is refining. And refining is basically where they take the pure metal away from the impurities. So the low boiling point metals are refined through distillation, and then they use an inclined table to separate the low melting metals away from the higher melting impurities. Also, you might see electrolysis done to refine our metals. So here's some a nugget of copper, a gold nugget, and some iron ore, just to kind of show some of their natural forms. I've always thought natural copper is just so beautiful. Okay, so we're going to go ahead and start by talking about the isolation of iron. Now, I highly recommend, if you're really interested in this, that you read your book a little bit more. There's also a link from OpenStax that shows a video of some of the smelting process. It's an interesting process, but my notes here are more bullet points and kind of a summary. The book was a lot more in-depth, kind of like in chapter 18, with how in-depth it went with some stuff. So the first step is the iron ore. So remember, iron tends to be in its oxidized form. It's heated in air to remove water and then to decompose any carbonates into oxides and convert those sulfides into oxides as well. So that way we get all iron oxides. The oxides from there are reduced in a blast furnace. So it's put in a blast furnace, and then in the very top of the furnace, roasted ore, coke, and limestone are continuously introduced into the top. At the bottom of the furnace is where the molten iron and slag are collected. And then towards the bottom, there's air that's blown into the bottom of the furnace, and this is there to oxidize the coke to carbon dioxide, which from there passes through white hot coke and reduces it to carbon monoxide. And this carbon monoxide now acts as a reducing agent for the upper regions of the furnace. The slag is formed in the middle of the furnace from the limestone that's introduced, decomposing to calcium oxide, which will then combine with silica and the silicates from the ore that from earlier to form the slag, which will then melt with the iron, and it's less dense, so it's going to float on top of the molten iron and in turn protects it from oxidizing. So everything that's put in this furnace has a purpose. The slag and the iron are then collected, and the iron can be casted or transferred to a steel making plant. Most iron itself is refined and converted to steel by adding different substances to make it an alloy for whatever uses that they need it for. Some things that are added are manganese, chromium, nickel, tungsten, molybdenum, or vanadium. Carbon can also be used in low percentages, but you can't do too much, otherwise carbon could make it too brittle. So this is a schematic of a blast furnace. If you go on to your book, whether online or physical book, whatever, it's a lot clearer, but you can see the different reactions at the different heights in the furnace, which is pretty cool. These things are very big. We're talking like almost 100 feet tall. You can see where the ore, coke, and limestone are introduced in the top, and then where the slag and the iron are collected at the bottom, where the air goes in. And just as you go down the furnace, there's different reactions that are happening to eventually get us to that molten iron. And this is showing some of this molten iron being cast into steel. So your book has a link to the animation of steel, showing you the animation of steel making. So show when they take the iron and make it into steel. It's pretty cool. It's only like a 2-minute video. So the next metal we're going to talk about is the isolation of copper. So the most important ores with copper have copper sulfides. And don't forget, a lot of copper we can get in its elemental form. So this is talking about the copper oxides and sulfides. It can be found as tenorite, which is CuO, or copper hydroxycarbonates like malachite. But the most important are the copper sulfides. So first, the sulfide ore is roasted, and this is going to remove part of the sulfur as sulfur dioxide, but not all of it, which is what I thought was really interesting. The remaining mixture, which now has copper 1 sulfide, as well as iron 2 sulfide, iron 2 oxide, and silicon dioxide, is then mixed with limestone. Limestone is used as flux, and a flux is a material that aids in the removal of impurities, and then it's heated. So this forms molten slag, and the iron in silica then is removed by acid-base reactions, where silicon dioxide acts as a Lewis acid. So the calcium carbonate, for instance, is reacting with silicon dioxide to form this calcium silicate and carbon dioxide gas, so they can remove that. And then the iron 2 oxide. This is a solid, I forgot to put in. And the silicon dioxide then makes this iron silicate. That is a liquid that can also be removed. So then the remaining copper 1 sulfide is then reduced by blowing air through it. So it's in a molten form. We blow some air through it. Part of it then is converted to copper 1 oxide, which then reacts with the remaining copper 1 sulfide to form metallic copper, which I thought was really cool. So we take some of this copper 1 sulfide, give it some oxygen, and we get some copper 1 oxide and sulfur dioxide. And then now this copper 1 oxide will then react with copper 1 sulfide to give us metallic copper in its molten form and SO2. So one thing that's interesting is this copper that is obtained in this manner is called blister copper. And this is what it looks like. And because of its characteristic appearance, that's why we call it blister copper. It's actually kind of impure, but here it'll be cast into plates, which can be used as anodes in electrolytic refining of the metal. which we talked about in electrochemistry. So the next one we're going to talk about is silver. So silver is often found in nuggets, veins, and different deposits, so it's all over the place. One thing I thought was an interesting little factoid was platinum was discovered because Spanish explorers in Central America mistook platinum nuggets for silver, and it turns out it was platinum. When it's not in the form of nuggets, hydrometallurgy is used to separate silver from the ores. So hydrology essentially, and this is where we separate a metal from a mixture by converting it into soluble ions first, and then we extract them and reduce them to a precipitate of our pure metal. And alkali metal cyanides tend to be used for silver. So we want to form the soluble dicyanoargentate. Yeah. So I'll show you the equation. So we have our silver, which, keep in mind, it's in this ore. Maybe it's like a vein or something. We can't just pull it out. So we add some aqueous cyanide with oxygen and water. And we make this complex. And some hydroxide. But there's our soluble ion that we want. Another one that might happen when we have a silver ore. Ag2S. So now this one's an ore instead of just some pure silver. Same thing with the cyanide ion plus oxygen and water. And then we get the ion, silver cyanide thing. In this case, we also get elemental sulfur and hydroxide. And then the last one would be using silver chloride. In this case, we can just go with the aqueous cyanide. And this is a good old substitution reaction. Oops. And Cl minus. So all of them make this, let's see, I'm going to try the name again. Dicyanoargentate 1 ion. And we'll talk about actually that type of name in the next section. So from here, this dicyanoargentate 1 ion, we take it and we react it with some zinc. Zinc or iron 2 are used, which then serves as a reducing agent to give us solid silver. And then we have the zinc CN4 2 minus. And that gives us our solid silver. So here's some free silver. In A, we see some nuggets, and B, we see a silver vein. Silver is one of my favorite metals. I wear a lot of silver jewelry because it's cheaper than gold and platinum and palladium, but unfortunately it's a lot more malleable, so it bends a lot easier and can morph. So like, for instance, I'm not a fan of the latest trend where they've been putting diamonds in silver, just because silver is fairly soft in comparison to gold and platinum. So those prongs can bend very easy, and it can warp very easily, and you can potentially lose the diamonds or whatever stones are in it. But I love just plain silver jewelry. Like I always wear, almost always am wearing a tortoise, a sterling silver tortoise on a chain is my good luck charm that I've worn him since my second year of undergrad, so I've worn him for a very long time. So let's look at an example. We're showed one of the steps for refining silver and involves converting silver into dicyanoargin, argin, argin, arginate. It's not argentate, it's arginate. There's a typo in my book. And then we want to know why we have to have oxygen present to carry out the reaction and why it's not just seen as that second reaction. And that's because we need to have charge balance. The silver atom is being oxidized from 0 to +1. So you can see the silver here is going from 0, and then it has an oxidation state of +1. Nothing's happening to the oxidation state of any of the cyanide at all. So the hydrogen doesn't change, so the oxygen has to be changing in its oxidation state. So if one thing is being oxidized, as the silver is, something has to be reduced. So oxygen is there to be an oxidizing agent, and to then reduce from the 0 oxidation state as O2 to the 2- state. So yeah, well, that's why we need it. If we can't have it as that second reaction because there's nothing to reduce. So now we're going to talk about some transition metal compounds, and this is probably going to blow a lot of minds. Transition metals can bond for simple compounds anywhere from an ionic to a covalent compound. When you have a lower oxidation state, you tend to have an ionic compound, whereas higher oxidation states tend to form covalent compounds or polyatomic ions. So yes, everything you learned from, was it chapter like 4, is kind of a lie. That you can have covalent compounds with metals, but they're transition metals in them. So let's start by talking about some halides. Anhydrous, meaning no water halides, we can make by direct reaction of a metal with hydrogen. So for instance, we take some iron and react it with some chlorine gas, and we can make iron 3 chloride. Now, if we were to take a metal halide and heat it with some additional metal, we can form a metal halide that has a lower oxidation state. And the amounts of the halogen, as well as the metal that you're looking at, and the oxidizing strength of the halogen are going to determine the stoichiometry. So, for instance, if we take our iron metal and we react it with 2 iron 3 chlorides, we get iron 2 chloride. So it's kind of an interesting thing that these metals can do. If we take a hydrohalic acid and we add it to a carbonate, a hydroxide, or an oxide, we can actually prepare stable water solutions of the metal halides from the first transition series. So for instance, if we take some nickel carbonate and gives it some hydrofluoric acid, we can make this nickel 2 fluoride plus water plus CO2. Or if we take a cobalt 2 hydroxide and react it with some hydrobromic acid, we get this cobalt 2 bromide and water. FTS I have for meaning first transition series. I was getting tired of typing the whole thing. But the first transition series metals can dissolve in acid and they will form hydrogen gas and a salt solution. So for example, if we take some chromium, throw it in some hydrochloric acid, we make chromium 2 chloride and hydrogen gas. So one of the way that we can tell what type of bond is made is our bond polarity. Remember, if you remember from before, this depends on the electronegativities of your atoms that are in your compound, but here it also depends on the oxidation state of the transition metal, because this is going to determine how the electrons are distributed. And one thing to remember is that no bond is 100% ionic. So back when we first, in Chem 2A, when you would calculate based off of the electronegativity differences what type of bond it was, remember there was like different numbers that you could get. So like an ionic bond had like 2.4 and above, but so you could have like these bonds that weren't like purely ionic because there's still some closeness in their electronegativities. So it's one thing to keep in mind. Now, if we react some metal tetrahalides with water, this is one way to show their covalent behavior because they're going to create a hydrohalic acid and a metal oxide. So for instance, if we take some SiCl4 in its liquid form with some water, oops, not aqueous, that's liquid. Oops. We are going to make SiO2. So there's their metal oxide, which is a solid, and hydrochloric acid. So you can see that covalent behavior. If you did this with like titanium tetrachloride, it would do the same type of thing and make titanium dioxide and hydrochloric acid. Oxides. So the bonding nature to make an oxide is actually going to be determined by the metal's oxidation state. When you have a lower oxidation state in your metal ion, you're going to have a more ionic bond because the metals have a lower electronegativity value than oxygen. But when you're at a higher oxidation state, this is going to be a more covalent bond because the electronegativities are closer to oxygen, so you're more likely to have sharing of electrons. Our first transition series oxides can be prepared by heating them in air or by heating their hydroxide, their carbonate, or their oxalate in an inert atmosphere. Most transition metal oxides are not soluble in water, but they can react with acids and some bases. When you have a low oxidation state metal, these tend to be basic, whereas the higher oxidation state metal oxides are acidic, and the intermediate ones that have an oxidation state around 4+ tend to be amphoteric. So if you remember, amphoteric means it can act as an acid or a base. You can see some example equations in your book. Hydroxides. Now, hydroxides are interesting. When you take a soluble hydroxide and add it to an aqueous first transition series metal salt, you make this gelatinous precipitate. For example, if we take some take some cobalt 2+ aqueous into some hydroxide, we make COOH2 solid. And these precipitates tend to either be hydroxides that have the transition metal ion, or they can be hydroxide ions in water that are coordinated to the metal, or they could be hydrated oxides that are composed of the metal ion, oxide ions, and water of hydrations. Now, hydrated oxides technically are not hydroxides, but both them and hydroxides react with acids to form salts and water, so they're included in this. So an example of the second one would be, we take some iron 3+ and react it with OH- plus however many, that's what this N means, H2Os. This is because of the hydration. We make this iron oxide hydrate thing. Fe2O3 N plus 3 H2O. So there's an example of a hydrated oxide. Carbonates. Most of our first transition series metals are going to form insoluble carbonates. One way to make them is by adding a soluble carbonate salt to a metal salt solution. For instance, if we take some aqueous nickel and give it to an aqueous carbonate solution, we can make this nickel carbonate solid. Our transition metal carbonates react similar to the active metal carbonates, so you can refer back to chapter 18, but the basis is that they react with acids to form salts, carbon dioxide, and water, and they can decompose to their metal oxides with heat. There are some other salts. For instance, the first transition series salt preparation in general is similar to main group salt preparation. So you can take your metal that is more active than hydrogen with corresponding acid. So for instance, scandium, if we take some scandium solid and react it with hydrobromic acid, we can make the scandium 3 bromide salts and hydrogen gas. We can also do prepare salts by reacting their oxide, hydroxide, or carbonate with acid. So for instance, if we take some nickel hydroxide, that is a solid, and give it some acid, and some perchlorate. Well, that acid is from the perchlorate. We get some aqueous nickel here. So now we've made this aqueous nickel perchlorate salt. And then we can also do substitution reactions to make some insoluble salts. For instance, we take some aqueous barium and some Cl- with some aqueous potassium and some chromate. So we're making a chromate salt. And this gives us barium chromate. Plus some potassium and plus some chloride. So superconductors are something that's definitely an emerging science and becoming very, very popular in research in the field of inorganic chemistry. And these are substances that conduct electricity with no resistance. So that means there's no energy loss when electricity is transmitted, which could really reduce the cost of electricity. But one of the problems is that some of the most common commercial superconductors don't become superconductors until they're cooled below 23 Kelvin. That's negative 250 degrees Celsius. So liquid helium generally has to be used, but it's very expensive and hard to use. So this really has deterred the use of superconductors. But in the 1980s, there was some characterization done on some compounds that exhibit superconductivity at temperatures above 90 Kelvin, which is considered a much higher temperature because you can actually use like liquid nitrogen for this. So a lot of times they have yttrium, which is one of our rare earth elements, or barium with barium and copper in a 1 to 2 to 3 ratio. So that's this this formula you see here, this YBA2Cu3O7. And so again, we can use liquid nitrogen to cool these materials, which is much more common and much cheaper to use. Literally, the cooling cost is about 1,000 times lower than liquid helium. Unfortunately, though, they're very fragile and brittle, which is what's hampering their commercial applications. But there's a lot of potential here, and there's researchers looking to improve the processes. Um, but some, like if we were able to have some superconducting transition lines, we could carry current for hundreds of miles with literally no power loss because there's no resistance in the wires. So we could have like electricity generation stations in remote areas, far from population centers, and near natural resources that are needed for power production. So actually, the first project that demonstrated this viability was established in New York in 2008. So researchers are trying to use this technology for other applications like smaller and more powerful microchips, as well as high temperature superconductors for generating magnetic fields for things like medical devices, magnetic levitation trains, and containment fields for nuclear fusion reactors. So you can see in A the maglev, the magnetic levitation train. That's in development, as well as in B, they're showing a magnet being levitated using this as by a superconductor.